We are going to conduct some imaginary experiments on photons. And one of the devices we will use for our imaginary experiments is your phone or laptop. Consider the screen on which you are watching this video lesson. The screen is a source of light. It emits photons which travel away from the screen and reach your eye. These photons have a quantum property called polarization. This property is an angle, the angle of polarization. Photons are polarized at an angle theta. When polarization angle theta is 0, we call it horizontal polarization. When polarization angle theta is 90 degrees, we call it vertical polarization. Theta can also be some angle other than 0 or 90. In classical computers, we know about the concept of bits. A Boolean value of false is encoded as a bit value of 0, which is represented at a circuit level with a 0-volt potential. A Boolean value of true is encoded as a bit value of 1, which is often represented at a circuit level with a positive 5-volt potential. In quantum computers, we have quantum bits or qubits. I had mentioned earlier that photon polarization behaves exactly like qubits. So let's define vertical polarization to represent a qubit value of 1 and horizontal polarization to represent a qubit value of 0. We could have defined any two angles that are separated by 90 degrees as qubits 1 and 0. In this case, we have chosen 90 degrees. That is vertical polarization for representing qubit value 1, and 0 degrees, that is horizontal polarization for representing qubit value 0. Now let's use your screen, this screen where you're watching this video, in our virtual experiments. See this rectangle here? Assume for this virtual experiment that it is a source of vertically polarized photons. That is, vertically polarized photons are produced by this rectangular patch on your screen. The photons are directed away from your screen and toward your eyes. Next, we place a vertically polarized filter over this light source. This inner rectangle you see here represents the vertically polarizing filter. The filter appears to be completely transparent. That is because a vertically polarizing filter allows all photons which are vertically polarized to pass through. In other words, a vertically polarizing filter is completely transparent to vertically polarized photons. There are two arrows you see in this picture. This inner arrow is the direction of polarization of the filter. The outer arrow here is the direction of polarization of the light source. Next, we replace the vertically polarizing filter with a horizontally polarizing filter. A horizontally polarizing filter is not made of some strange substance that is different from a vertically polarizing filter. They are both essentially the same. If we rotate the vertically polarizing filter by 90 degrees, we get a horizontally polarizing filter. As you can see here, the light source is still vertically polarized. That is, it continues to emit photons that are vertically polarized. But the polarizing filter we placed on top has been rotated so that it is horizontal. That is, we have placed a horizontally polarizing filter on top of the light source. This arrow, which is horizontal, indicates the orientation of the filter. The polarizing filter in this configuration is completely opaque to the photons. That is why it appears black. The main rule is this. When a polarizing filter is aligned in the same direction as a photon, the photon always passes through. Earlier, both the photons and the filter were vertical, so the photons pass through. Instead, as shown here, if the polarizing filter is at 90 degrees angle to the photon's polarization, then the photon is always blocked by the filter. In the diagram shown here, the light source is producing vertically polarized photons, but the filter is now horizontal. That is, the filter and the photons are at 90 degrees to each other. So the photons are always blocked. The filter in this configuration is opaque, so it appears black. Next, we rotate the filter so that it is oriented at 45 degrees as shown here. In this case, 50% of the photons pass through and the remaining 50% are blocked. That is, speaking in aggregates, half the photons pass through and the rest are blocked. But if we look at this configuration from the point of view of a single photon, then we say that a photon has a probability of 0.5 of passing through and a probability of 0.5 of being blocked. Since half the light gets through, the filter appears grey in this picture. In general, if the photons and the filter are a small angle apart, say 10 degrees, then most of the light would pass through. And if the angle between the filter and the photon polarization was large, say 80 degrees, then very little light will get through. You will shortly be invited to rate this course. Please provide an honest review to help future students decide if this course will be right for them. According to Udemy, the average rating for courses in quantum computing is 4.4. If your rating is below average, it indicates that your experience with this course is negative and you wish to dissuade other students from enrolling in this course. Conversely, if you rate this course above average, then it indicates that you are happy with this course and believe it will be useful for other students. Quantum physics is difficult to understand. As the famous physicist Richard Feynman said, "I think I can safely say that nobody understands quantum mechanics." So, if you are unsure, you can wait until you finish the course before submitting a rating.